Today I find a suspicious SMPS driver or SMPS. You can see some marking text here, Angel Lighting Lounge. I don't know. I don't know the company name. 100% power copper parts premium quality. What do they mean by this statement? Is the transformer wound with 100% pure copper? This seems to be some kind of type number or marking. Superior driver, some marking here, and nothing on the other side. It's just the same. So let's take a look at the power, but let's also take a on the side of the box. You can see it can power, or it can output 12 volts. It can give you 5 amps, 60 watts. Well, this tiny SMPS will give you 60 watts of power, and it looks quite tiny, and it is not much heavy. It is light. So I guess they are using tiny transformer with tiny or thin wire, and if it is really supplying this much power, the transformer will just completely melt, blast, evaporate, or something like this. So let's take a look at the power supply. Here's the power supply. It is in aluminum housing. You can see the look at the transformer. The transformer is quite tiny, as I said. This is the secondary side, this is the primary side, and let's look at the marking of it. Model number, input, output is 12 volts 5 amp, which is quite a lot, and here it says 60 watts maximum, and there is no screw from this side. I don't see any transistor, so it might be SMD. The diode is also SMD, I guess, but there seems to be very few SMD component. So can I open it somehow? So this cover just clicks in. You can see the first component, the transformer, which is quite tiny. You can see the primary smoothing capacitor, 1000 microfarad, 16 volts, OK for 12 volts, LED for indication or for to tell you that it is working. The primary smoothing capacitor looks quite tiny as well, 10 UF 400 volts. You can see the auxiliary rectifying capacitor, 10 microfarad, 50 volts. Some other capacitor may be in the snubber network to protect the transistor from over spikes or over voltage spikes. This capacitor, which doesn't seems to be a CY1 capacitor, but on the board you can see the marking of CY1 capacitor, but they may have put some random capacitor. Let's take a look at the other side of the board, because there is little to nothing on this side of the board. So this is the board from the other side. It uses a switch which has built-in high frequency high voltage transistor. There's big SMD diode, maybe synchronous. Let's look at the marking, SS310. So this chip is going to be handling 60 watts, and there's nothing, no heatsink, no thermal, basically think thermal coupling. So it is going to be getting very hot, and I can see one more disaster, this thin track on the board. So there is no fuse. There is this rectifier which straight goes to the smoothing capacitor, and the smoothing capacitor is tiny, but it needs a inrush resistor, but there is none, so it doesn't look nice for 60 watts. Well, for 60 watts it needs much more component, interference filtering, and much more, but there is little to none, so I highly doubt this one. Well, the power supply is rated for 60 watts, but looking at the transformer secondary winding, the winding seems small, and if it handles 5 amp, then the winding is just going to be very hot, and it is going to melt the transformer, which is quite dangerous. So now let's put the cover back. Okay, so first let's try to measure the voltage, and then I will try to measure the current capability of it. So first let's measure the voltage. Now it is working. The voltage seems to be 11.6, so it is not complete 12 volts but close to it, and I had not seen any optocoupler in it, so it is basically sensing the current and voltage on the second primary side, not on the secondary side. So now let's try to load it. I have a test load which can go up to 2.5 amp, and this power supply should be able to handle up to 2.5 amps at 12 volts. The current is set to the lowest current, which is 100 milliampere. So I'm going to increase it 1 ampere, and now it is tripping. Well, it supplies up to 1 amp and then it trips. This 5 ampere 60 watt has to be fake, and it is also using a chip, and of course a chip alone cannot basically power up to 60 watts. The voltage sensing is on the secondary side, so thus the voltage drop under the load and then it trips. So let's see. This is on the voltage mode. You can see the voltage here, 12 volts now. Now the voltage decreases, now it increases a bit, and then it trips. So at full current 1 amp, that gives you the maximum voltage 12 volts, and then it trips. Well, I've drawn this schematic here and it makes sense, but there is one section which doesn't make any sense, which is the input section. There is no fuse and no interference filtering, which is completely rubbish, which is basically horrific. If the chip goes short, the bridge rectifier also goes short, and then there is very high current flowing, which shorts the main, and you rely really on the breaker and the trend track and the wire. So this is really horrific. There is this chip which is DP2701F, which is 12 watts chip, and this power supply can give you only 12 watts, not 60 watts. But the design of it really makes sense. Basically there is this chip to transformer, and so basically the chip starts up via this very high resistance resistor, which is 1.5 mega ohm. It charges this capacitor, and when this capacitor reaches some voltage, the chip starts to switch, and the auxiliary winding generates some voltage, which is rectified by this diode, and the chip uses that power. So basically when the chip starts to switch, so when the MOSFET inside the chip is on, the polarity of the transformer is this, and the transformer has an air gap. So basically when the MOSFET is on, the air gap is accumulating energy, and when the MOSFET turns on, the polarity of the winding switches. So basically when the MOSFET inside the chip is on, the polarity of the primary winding is this, but the polarity on the secondary winding is going to be this, positive here and negative here. So this diode doesn't conduct, and this diode will also not conduct because the polarity is in reverse. Basically the positive is here, negative is here. So when the MOSFET turns off, the polarity changes like this, and the de-energization of the core starts, and when the polarity reverses, the polarity on these two windings will also reverse. So this one will become positive and this one will become negative, this one will become positive and this one will become negative. This diode and this diode will start to conduct. They will charge their capacitor and power the load, and that's how it is working. The voltage sensing, or for the voltage sensing, the chip is using some kind of resistor divider, 17 kilo ohm and 1.5 kilo ohm. These two windings have some ratio in common. So basically the reference, basically when the chip hits its reference voltage, like maybe 12 volt or 13 volt or something like this, the chip knows that there is going to be 12 volts on the secondary side. So that's how it is working. So now let's try to make some oscilloscope measurement. Let's try to connect ground of the oscilloscope to ground. Let's probe at the switching pin of the chip and the current sensing pin of the chip. After these two measurements, I will also like to probe at the auxiliary winding. Here is my oscilloscope. The blue line is the switching pin of the chip. The yellow line is the current sensing shunt, across the current sensing shunt. So let's try to turn it on. Hope for no explosion again. You can see the switching waveform, and there is a lot of interference, and you can also see the current or sensing shunt. If I increase the voltage a bit, you can see how the current increases. And if I just probe at the switching signal, you can see with no load, with some load. You can see now the transistor is on for longer time, and there is high voltage. Let's look at the auxiliary winding. The ground of the oscilloscope probe is at the ground. I will just connect my oscilloscope probe here. Now this is the auxiliary winding waveform. So let's turn it on. Now here you can see the waveform. And again here you can see, here the transistor is on, here the diode is conducting in the secondary side. Let's also try to measure the frequency, because here the frequency measurement is wrong. Let's try to stop it, and now measure the frequency. It seems to be 57.8 kilohertz.